Valence bond theory does a good job of explaining molecular geometry, but doesn't account for some molecular properties, such as magnetism. Molecular orbital theory, or MO theory, is a different quantum mechanical approach to explain the bonding of molecules. We'll have 3 lectures over MO theory, with the first one explaining the fundamentals and the diagrams used to show the electron placement. Let's begin. We've learned that molecular oxygen has a linear Lewis structure with sp2 hybridization to accommodate the 3 electron groups around each oxygen. The Lewis structure and valence bond theory imply that all electrons are paired, making it a diamagnetic material that should be slightly repelled by a magnetic field. However, you can pour liquid molecular oxygen between 2 powerful magnets, and the magnets will capture it. This tells us that the electrons are not all paired. Rather, molecular oxygen has unpaired electrons that are attracted to the magnetic field. Given that the Lewis structure and valence bond theory fail to predict the paramagnetism of molecular oxygen, we have to turn to molecular orbital theory, another quantum mechanical description that, while more complicated than valence bond theory, manages to account for this observed physical property. MO theory proposes that the wave functions of atomic orbitals from different atoms combine to form molecular orbitals that are delocalized or shared over the entirety of the resulting molecule. Just like valence bond theory, the number of atomic orbitals that combine will give the same number of molecular orbitals, but half of them will be lower in energy, which is ideal, and half of the molecular orbitals will be higher in energy. Let's look at some waves to understand why. If we think about the properties of a 2-dimensional wave, we can classify the amplitude with plus and minus signs for an amplitude above or below the axis, respectively. Orbitals are 3-dimensional waves, so we can think of combining s orbitals in an additive or subtractive fashion. The p orbitals always have a plus and minus side. Depending on whether we're overlapping 2 positive sides or a positive and negative side of a p orbital, we can get constructive or destructive interference. Let's consider the additive and subtractive combination of s orbitals here and hold the p orbital discussion for the next lecture. When adding 2 atomic orbitals together, we'll get 2 molecular orbitals. We see that when 2 hydrogen atoms come together, the 1s orbitals from each undergo an additive combination to form a sigma 1s bonding orbital, which has the highest probability of electron density along the internuclear axis, has lower energy than the 1s atomic orbitals, and if occupied by electrons, forms a sigma bond. The same 2 atomic orbitals also undergo a subtractive combination to form a sigma star 1s anti-bonding orbital, which has a node, or region of 0 probability of electron density, between the nuclei, and has higher energy than the 1s atomic energy level. Rather than drawing out the orbitals every time, we can simplify this by building a molecular orbital diagram. A molecular orbital diagram shows how the molecular orbitals are populated with electrons. The atomic orbitals are written to either side, and the linear combination of atomic orbitals gives rise to the molecular orbitals shown in the middle. The electrons from the atomic orbitals are used to fill the lowest energy levels of the molecular orbitals first, following the Aufbau principle. In the hydrogen molecule, the MO diagram places 2 electrons in the bonding sigma 1s orbital and no electrons in the sigma star 1s orbital. The MO configuration for H2 is sigma 1s superscript 2. When you see MO diagrams, they'll most likely be very minimalist, like the one shown here for H2. The atomic and molecular orbitals will be labeled, and the electrons will be written following all of the same rules for filling atomic orbitals. Namely, you'll still need to use the Aufbau principle to fill the lowest energy orbitals first. You'll still only put 2 electrons in each orbital following the Pauli exclusion principle, and you'll fill all orbitals of the same energy with a single electron before going back and adding more electrons that are spin paired. To keep the MO diagrams as simple as possible, we'll only consider the valence electrons and the valence orbitals. Let's look at another MO diagram. What if we were to combine a hydrogen atom with 1 electron, on the left, with a hydride ion containing 2 electrons, shown on the right? We would still place 2 electrons in the sigma 1s molecular orbital, but now we have a third electron that has to go into the anti-bonding sigma 1s orbital. Anytime you have 2 electrons showing up in an anti-bonding molecular orbital, it will destabilize the molecule. Suppose we try to build a molecule using the noble gas helium. The hypothetical helium molecule uses the same basic MO diagram as hydrogen, but with 4 valence electrons. 2 electrons occupy the bonding orbital, and 2 electrons occupy the anti-bonding orbital. Because we have the same number of electrons in the bonding and anti-bonding orbitals, no bond can form. This explains why molecular helium is impossible to make. What would happen if we removed an electron, though? Taking just 1 electron from the anti-bonding orbital stabilizes the molecule enough for the diatomic helium cation to form He2+. Now we have enough data on molecular orbitals to put it all together. Let's do that. If we consider the sequential addition of electrons to a 1s-1s molecular orbital diagram, we see that we can form a bond all the way up to the completely destabilized hypothetical helium molecule. Let's collect this information in a data table to see if a pattern emerges. Summarizing the data for the molecules, the number of electrons in the bonding orbitals and the number of electrons in the anti-bonding orbitals, we see that we can actually calculate the bond order of a molecule. Specifically, we'll subtract the number of electrons in the anti-bonding molecular orbital, which destabilizes the molecule, from the number of electrons in the bonding orbital, which stabilizes the molecule because electrons are in a lower energy molecular orbital. The result is divided by 2, accounting for the fact we need 2 electrons to be shared per bond. For the series of molecules shown here, we see the hydrogen molecule has the highest bond order with a single bond. The H2+ and He2+ cations are next with a 1/2 bond order, and the helium molecule has a bond order of 0, meaning a bond isn't formed. The goal here is to get the highest bond order possible, which infers greater stability over the entire molecule. Here's one for you to try. Given the molecular orbital diagram for the H2- ion, can it exist according to MO theory? We have 3 electrons, 1 from a hydrogen atom and 2 from a hydride ion, H-. Using the MO diagram for H2, this gives us a molecular electron configuration of sigma 1s2, sigma star 1s1 with a bond order of 1/2 times 2 - 1 equals 0.5. Therefore, we conclude that the H2- ion can form but is less stable than H2. This concludes our first MO lecture. I will hold the parting thoughts from the authors for the third and final lecture in the series.